we're drifting into one of space's most fascinating mysteries, a story that unfolds in the vast emptiness between Mars and Jupiter, where millions of ancient remnants tell a tale of cosmic violence, planetary migration, and the delicate dance that shaped our solar system. What if I told you that floating in the darkness between the red planet and the gas giant lies a graveyard of failed worlds? A collection of rocky fragments that holds the secrets to understanding how planets are born, how they die, and how the gravitational ballet of giant worlds can reshape entire regions of space. This is the story of the asteroid belt, and it's far more dramatic than you might imagine. Feel free to let me know where in the world you're listening from tonight. There's something beautifully humbling about contemplating these ancient cosmic stories while we're all scattered across our small blue planet, each of us under the same starry sky that has witnessed every moment of this 4.5 billion year saga. The visuals are here to guide you, but there's absolutely no problem if you find yourself drifting off midway through this cosmic tale. Sometimes the best way to absorb the mysteries of space is to let your mind float freely among the stars. If you find comfort in these gentle explorations of our universe's deepest secrets, I'd be grateful if you'd consider subscribing and giving this video a gentle tap of approval. It helps the algorithm find more curious souls like us who hunger for understanding the elegant mechanics of the cosmos. Your support means the world to me and helps me continue crafting these long-form journeys into the heart of astronomical wonder. Now let me paint you a picture of our solar system as it exists today. Imagine standing on a cosmic observation deck, looking down at the elegant arrangement of planets orbiting our Sun. You see Mercury, Venus, Earth, and Mars hugging close to our star, their rocky surfaces baked by solar radiation. Then there's a gap, a seemingly empty stretch of space that extends for millions of kilometers before you encounter the majestic gas giants Jupiter, Saturn, Uranus, and Neptune. But that gap isn't empty at all. It's populated by countless rocky fragments, irregular chunks of stone and metal that tumble through the darkness in elliptical orbits around our Sun. This is the asteroid belt, and it represents one of the most profound mysteries in planetary science. Why is there a belt of debris where, by all rights, there should be a planet? You see, according to our understanding of how solar systems form, that region between Mars and Jupiter should contain enough material to build a world perhaps as large as Earth itself. The spacing of the planets, the distribution of matter in our early solar nebula, everything points to the fact that a substantial planet should exist in that orbital zone. Instead, we find fragments, millions upon millions of them, ranging from house-sized boulders to Ceres, a dwarf planet that comprises nearly a third of the belt's total mass. The total mass of the entire asteroid belt is less than our moon. Think about that for a moment. All those countless rocks, all those dramatic impacts we see in science fiction movies, all those mining operations imagined in futuristic stories, and the entire collection of debris weighs less than the celestial body that lights our night sky. It's as if someone took a planet and removed 99.9% of its material, leaving behind only the crumbs. This wasn't always the case. The story of the asteroid belt is not one of emptiness, but of loss. It's a tale of what might have been, of planetary dreams interrupted by the gravitational tyranny of Jupiter. 4.5 billion years ago, when our solar system was young and the planets were still forming, That region between Mars and Jupiter was alive with possibility. Picture the early solar nebula, a swirling disk of gas and dust surrounding our newborn sun. Within this disk, particles began to stick together through electrostatic forces, growing from microscopic specks into pebbles, then boulders, then planetesimals. It was a process of gradual accumulation, where gravity became the dominant force shaping these growing worlds. In the inner solar system, closer to the sun where temperatures were high, only rocky materials could condense. These formed the terrestrial planets we know today. But farther out, beyond what astronomers call the snow line, water could freeze into ice, providing additional building material for the growing worlds. This is where the asteroid belt region found itself, right at the boundary between the hot inner system and the cold outer reaches. The conditions were perfect for planet formation. There was abundant material, the right temperature gradient, and sufficient time for gravitational accumulation to work its magic. Computer simulations suggest that the original asteroid belt region may have contained mass equivalent to several Earth masses worth of planetesimals. The raw materials were there, waiting to be assembled into what could have been a magnificent world. But something went wrong. Catastrophically wrong. As the planets grew, Jupiter emerged as the dominant force in the outer solar system. This massive world, containing more mass than all the other planets combined, began to exert its gravitational influence across vast distances. Like a cosmic bully, Jupiter's gravity reached into the asteroid belt region and began to stir things up. The process wasn't violent in the way we might imagine. There were no dramatic explosions or sudden catastrophes. Instead, Jupiter's influence worked slowly and inexorably, changing the orbital dynamics of the planetesimals trying to form in the belt region. What should have been circular, stable orbits became elongated and chaotic. Collision velocities increased from gentle bumps that allowed accretion to devastating smashes that shattered existing bodies. This is where the story becomes truly fascinating. Recent research has revealed that Jupiter didn't just disrupt the asteroid belt from its current position. The giant planet actually migrated inward during the early solar system's formation, moving closer to the Sun before eventually settling into its present orbit. This migration, known as the Grand Tack model, fundamentally reshaped the entire inner solar system. Imagine Jupiter as a cosmic wrecking ball, slowly moving inward through the solar nebula. As it migrated, it crossed the asteroid belt region not once, but twice. First on its way inward, then again as it migrated back outward when it became locked in orbital resonance with Saturn. Each passage scattered planetesimals, preventing them from accumulating into larger bodies, and instead setting them on collision courses with each other. The gravitational perturbations from Jupiter's migration had another profound effect. They didn't just prevent new planets from forming, they actively depleted the region of most of its material. Computer simulations suggest that within about 1 million years of Jupiter's formation, most of the original material in the asteroid belt region was ejected from the area entirely. Some fragments were flung into the outer solar system, others crashed into the inner planets, and still others were cast out of the solar system altogether. This depletion was so severe that less than 0.1% of the original material remained. It's as if a cosmic vacuum cleaner had swept through the region, leaving behind only the smallest fragments that happened to find stable orbital niches where they could survive Jupiter's gravitational onslaught. But the story doesn't end with destruction. The asteroid belt we observe today is not simply the leftover debris from this ancient catastrophe. It's actually a refugee camp of sorts, populated by objects that originated from completely different regions of the solar system. Some asteroids were scattered inward from beyond Jupiter's orbit, carrying with them the primitive, carbon-rich materials that formed in the cold outer reaches of the solar nebula. Others were scattered outward from the inner solar system, bringing with them the dry, rocky compositions typical of the terrestrial planet region. This mixing process explains one of the most puzzling features of the modern asteroid belt, its compositional diversity. In the inner portions of the belt, we find mostly S-type asteroids, rocky bodies similar to the material that makes up the terrestrial planets. These are dry, processed objects that formed closer to the Sun where temperatures were too high for water ice to condense. Moving outward through the belt, we encounter increasing numbers of C-type asteroids, dark, carbon-rich bodies that contain significant amounts of water locked in their mineral structures. These objects clearly formed in much colder regions of the solar system, where organic compounds could condense and water could freeze into the growing planetesimals. This compositional gradient tells us that the asteroid belt is not a single population of objects, but rather a mixture of materials from across the solar system, brought together by the complex gravitational choreography of planetary migration. It's like finding Arctic penguins living alongside desert lizards, a clear sign that some powerful force has mixed up the natural order of things. The largest asteroids in the belt tell individual stories of this complex formation process. Ceres, now classified as a dwarf planet, appears to have formed much farther from the Sun, possibly in the region between Jupiter and Saturn. Its composition, rich in water ice and ammonia salts, suggests it originated in the cold outer solar system before being scattered inward to its current orbit. Vesta, the second largest asteroid, represents a different type of survivor. This battered world actually managed to differentiate during the early solar system, developing a metallic core, rocky mantle, and basaltic crust much like the terrestrial planets. It's essentially a protoplanet, a world that was well on its way to becoming a full-size planet before Jupiter's gravitational influence froze its development. The surface of Vesta bears the scars of this violent history. Massive impact basins, visible even from Earth-based telescopes, show where other large asteroids smashed into its surface with tremendous force. These impacts were so powerful that they blasted fragments of Vesta's crust into space, some of which eventually made their way to Earth as meteorites. By studying these meteorites in laboratories, scientists can piece together the story of Vesta's formation and the conditions that existed in the early asteroid belt. But perhaps the most remarkable aspect of asteroid belt formation is how it relates to the broader story of planetary system architecture. The presence of Jupiter in our solar system, and specifically its migration history, has shaped not just the asteroid belt, but the entire configuration of planets we see today. Without Jupiter's inward migration, Mars would likely be much larger than it is today. The red planet formed in the outer reaches of the terrestrial planet zone, where there should have been abundant material for building worlds. But Jupiter's presence scattered much of this material away, leaving Mars to form from the limited debris that remained. This is why Mars is smaller than Venus and Earth, despite forming farther from the Sun, where more building material should have been available. The asteroid belt formation story also helps explain why the terrestrial planets have the compositions they do. The mixing and scattering processes that created the belt also delivered water-rich materials from the outer solar system to the inner planets during their formation. Some of the water in Earth's oceans may have come from asteroids that were scattered inward during Jupiter's migration, carrying with them the precious H2O that makes our world habitable. This cosmic ballet of planetary migration and material redistribution wasn't unique to our solar system. Astronomers studying other star systems have found evidence for similar processes occurring around distant suns. Many exoplanetary systems show signs of giant planet migration, and some contain debris disks that may be analogous to our asteroid belt. Understanding how our own belt formed helps us interpret these observations and develop a more complete picture of how planetary systems evolve. The story of asteroid belt formation is ultimately a story about the delicate balance required for planetary formation. It shows us how the presence of giant planets can fundamentally alter the architecture of a solar system, preventing some worlds from forming while enabling the formation of others. It demonstrates the importance of timing in cosmic evolution, how the order and pace of planetary growth can determine which regions of a solar system become populated with planets and which become graveyards of planetary dreams. As we continue this journey through the asteroid belt's remarkable history, we'll explore the specific mechanisms that drove its formation, the evidence we've gathered from meteorites and space missions, and the ongoing processes that continue to shape this dynamic region of our solar system today. The mechanisms behind asteroid belt formation reveal themselves through some of the most elegant processes in planetary science. To truly understand how this cosmic refugee camp came to exist, we need to delve into the physics of planetary formation itself, where tiny dust grains somehow manage to overcome seemingly impossible odds to grow into worlds. In the beginning, our solar nebula was a swirling disk of gas and dust, with temperatures and densities that varied dramatically with distance from the young sun. Close to our star, the intense heat vaporized most materials, except for the most refractory substances, metals, and rocky silicates that could withstand the scorching environment. But farther out, beyond what scientists call the snow line, water could condense into ice, providing a crucial building material that would fundamentally alter the formation process. The asteroid belt region found itself in a unique position, straddling this boundary between the hot inner system and the cold outer reaches. This location should have been ideal for planet formation, combining the rocky materials that could survive closer to the sun with the icy components that condensed farther out. The stage was set for the creation of a substantial world, perhaps rivaling Earth in size and complexity. But the journey from dust to planet is fraught with challenges that most people never consider. When tiny particles first begin to stick together in the solar nebula, they rely on weak electrostatic forces and van der Waals interactions. These forces work well for microscopic grains, allowing them to form fluffy aggregates that drift through the nebula disk. But as these clumps grow larger, they face what planetary scientists call the meter-sized barrier. Objects that reach roughly a meter in diameter encounter a serious problem. They're too large to stick together efficiently through electrostatic forces, but too small for gravity to take over as the dominant binding force. Worse yet, they experience significant drag from the surrounding gas, causing them to spiral inward toward the sun on timescales much shorter than the millions of years needed for planetary formation. It's a cosmic catch-22 that should prevent most planetary systems from forming at all. The solution to this puzzle lies in a process called the streaming instability, one of the most beautiful mechanisms in all of astrophysics. When solid particles drift through the gaseous disk, they create subtle pressure variations in the surrounding gas. These pressure changes, in turn, affect the motion of nearby particles, creating a feedback loop that can lead to the spontaneous concentration of solids into dense filaments. Imagine watching a murmuration of starlings, where thousands of individual birds suddenly organize themselves into flowing, coherent patterns that ripple across the sky. The streaming instability works in a similar way, causing dispersed particles to self-organize into dense concentrations that can reach densities thousands of times greater than the surrounding gas. When these filaments become dense enough, gravity finally takes over, causing them to collapse into bound clusters that become the first planetesimals. These newborn planetesimals, typically ranging from a few kilometers to hundreds of kilometers in diameter, represent the true building blocks of planets. Unlike the fluffy dust aggregates that came before them, planetesimals are gravitationally bound objects that can survive collisions and continue growing through accretion. They're like cosmic seeds, containing within them the potential to grow into full-sized worlds given enough time and material. In the asteroid belt region, this process began promisingly. The streaming instability operated efficiently, creating numerous planetesimals that began the slow process of gravitational accumulation. Computer simulations suggest that within the first million years of solar system formation, the belt region contained planetesimals with a total mass several times that of Earth. These objects followed relatively circular orbits and collided with each other at gentle velocities that allowed them to stick together rather than shatter. But the formation of Jupiter changed everything. As the giant planet grew to its enormous size, its gravitational influence began to reach across the solar system, perturbing the orbits of planetesimals in the asteroid belt region. What had been circular, stable orbits became elliptical and chaotic. Collision velocities that had once been gentle enough to allow accretion suddenly became violent enough to cause destruction. This transition from accretion to erosion marks one of the most dramatic phase changes in the history of our solar system. In regions where collision velocities remained low, planetesimals continued to grow into larger and larger objects, eventually becoming the terrestrial planets we know today. But in the asteroid belt region, Jupiter's gravitational stirring raised collision velocities above the critical threshold, where destruction dominates over construction. The physics of this transition are surprisingly subtle. When two planetesimals collide at low velocity, their surfaces deform and interlock, allowing them to stick together despite the impact. It's similar to how two pieces of putty can merge when pressed together gently, but increase the collision velocity beyond a certain point, and the impact energy becomes sufficient to overcome the gravitational binding energy of the objects. Instead of merging, they shatter into fragments. This critical velocity depends on the size and composition of the colliding objects, but for typical asteroid belt materials, it lies somewhere around a few hundred meters per second. Below this threshold, collisions lead to growth. Above it, they lead to destruction. Jupiter's gravitational influence pushed collision velocities in the belt region well above this critical value, effectively switching off planet formation and beginning a process of gradual erosion. The erosion wasn't immediate or dramatic. Instead, it was a slow grinding process that played out over millions of years. Large planetesimals would collide and break apart into smaller fragments. These fragments would then collide with other objects, creating even smaller pieces. Over time, the size distribution of objects in the belt evolved from a few large planetesimals to many smaller asteroids. But Jupiter's influence went far beyond simply stirring up the asteroid belt. The giant planet was itself migrating during this crucial period, moving inward from its formation location at about 3.5 astronomical units to as close as 1.5 astronomical units from the Sun. This inward migration, driven by interactions with the gaseous disk, had profound consequences for the entire inner solar system. As Jupiter migrated inward, it passed through the asteroid belt region, dramatically altering the orbital dynamics of every object in its path. Planetesimals were scattered in all directions, some thrown into the inner solar system, others flung outward beyond Jupiter's orbit. The few objects that remained in the belt region found themselves on highly excited orbits with large eccentricities and inclinations. The story becomes even more complex when we consider Saturn's role in this cosmic drama. As Saturn grew to maturity, it eventually became massive enough to gravitationally capture Jupiter in what's known as a mean motion resonance. This resonance caused Jupiter's migration to reverse, sending the giant planet back outward toward its current orbital position. But the damage to the asteroid belt had already been done. During Jupiter's outward migration, it encountered a different population of objects, primitive bodies that had formed in the cold outer regions of the solar system. These carbon-rich, water-bearing objects were scattered inward, some finding stable orbits in the outer portions of the asteroid belt. This explains why the outer belt today is dominated by dark, primitive C-type asteroids, while the inner belt contains mostly the dry, rocky S-type objects. The compositional mixing that resulted from Jupiter's migration created the diverse asteroid population we observe today. It's as if ingredients from a cosmic recipe were thoroughly stirred together, creating a blend of materials from across the solar system. This mixing has proven invaluable for understanding the conditions that existed in different regions of the early solar nebula. Recent research has revealed that this migration scenario, known as the Grand Tack model, can explain numerous puzzling features of our solar system simultaneously. It accounts for the small mass of Mars, the compositional differences between the terrestrial planets, the structure of the asteroid belt, and even the delivery of water to the inner planets during the late stages of their formation. But the Grand Tack isn't the only mechanism that may have shaped asteroid belt formation. Alternative models, such as the Jupiter-Saturn chaotic excitation scenario, propose that resonant interactions between the two giant planets could have excited and depleted the primordial belt without requiring large-scale planetary migration. In this model, Jupiter and Saturn's orbits evolve into a near-resonant configuration that generates chaotic dynamics, stirring up the asteroid belt region and causing most of its mass to be lost through gravitational scattering. Even more radical is the possibility that the asteroid belt region was never massive to begin with. The empty primordial belt model suggests that very few planetesimals ever formed between Mars and Jupiter's present orbits. Instead, the belt we see today was populated entirely by objects scattered from other regions of the solar system during terrestrial planet formation and giant planet migration. This implantation model draws support from detailed studies of asteroid orbital dynamics and compositions. The evidence suggests that different types of asteroids were implanted from different source regions at different times, creating the complex population we observe today. S-type asteroids appear to have been scattered outward from the terrestrial planet region, while C-type asteroids were implanted from the outer solar system during the giant planet's formation and migration. Understanding which of these formation scenarios is correct has profound implications for our understanding of planetary system architecture. It affects our interpretation of exoplanetary systems, our models of terrestrial planet formation, and our estimates of how much water and other volatile materials were available in the inner solar system during Earth's formation. The timing of asteroid belt formation also provides crucial constraints on early solar system evolution. Analysis of meteorites from Vesta and other differentiated asteroids suggests that these objects formed and differentiated within the first few million years of solar system history. This rapid formation timeline indicates that the processes responsible for asteroid belt depletion and mixing must have operated very early, before the gaseous disk around the young sun had completely dissipated. The thermal evolution of early asteroids adds another layer of complexity to the formation story. Many of the larger asteroids experience significant internal heating during their first few tens of millions of years, driven primarily by the decay of short-lived radioactive isotopes like aluminum-26. This heating was sufficient to melt ice and drive differentiation in the largest objects, creating metallic cores surrounded by rocky mantles and basaltic crusts. The fact that objects like Vesta managed to differentiate tells us something important about the timing of belt formation. Differentiation requires that an object reach sufficient size before the short-lived radioactive heat sources decay away. This constrains the timescale for planetesimal formation and provides additional evidence that the asteroid belt region was initially much more massive than it is today. As we delve deeper into the mechanisms of asteroid belt formation, we begin to see how this seemingly empty region of space connects to virtually every aspect of solar system evolution. The belt's formation history influenced the growth of the terrestrial planets, the delivery of water and organic materials to Earth, and the overall architecture of planetary orbits we observe today. The story of how we've come to understand asteroid belt formation is as fascinating as the formation process itself. For centuries, astronomers looking up at the night sky had no idea that this region of scattered debris even existed. The discovery of the first asteroids came about almost by accident, during a systematic search for something entirely different. In 1801, Giuseppe Piazzi was methodically cataloguing stars from his observatory in Palermo when he noticed something unusual. One of the stellar objects in his telescope had moved slightly between observations. This wasn't the fixed point of light that characterized a distant star, but something much closer to home. Piazzi had discovered Ceres, the largest object in what we now call the asteroid belt, though he initially thought he had found a new comet. The discovery of Ceres was followed quickly by the detection of Pallas, Juno, and Vesta. These objects were initially classified as planets, bringing the total number of known planets in our solar system to 11. But as more and more of these small bodies were discovered in similar orbits, astronomers realized they represented an entirely new class of celestial objects. William Herschel coined the term asteroid, meaning star-like, to describe these mysterious wanderers. Early theories about the asteroid belt's origin were dominated by catastrophic thinking. Heinrich Olbers, who discovered both Pallas and Vesta, proposed that these objects were the remnants of a destroyed planet. The idea seemed logical at the time. Here was a region where a planet should exist according to Bode's law, a mathematical relationship that described planetary spacing. Yet instead of a single world, astronomers found countless fragments scattered across similar orbits. The destroyed planet hypothesis captured imaginations for generations. It painted a dramatic picture of some ancient cosmic catastrophe that had shattered a world, leaving behind the debris we observe today. Science fiction writers embraced this concept, creating stories about the lost planet Phaeton and the civilization that might have perished in its destruction. But as our understanding of physics and planetary formation improved, the catastrophic hypothesis began to unravel. The total mass of the asteroid belt was far too small to represent the remains of a planet-sized body. Even if you gathered every asteroid, every fragment, every grain of dust in the belt, you would have less material than exists in our moon. A planet large enough to fit the orbital spacing predicted by Bode's law would have contained hundreds of times more mass. The real breakthrough in understanding came with the development of computer simulations that could model the complex gravitational interactions in the early solar system. These simulations revealed that the asteroid belt's formation was not a story of destruction, but of prevention. Jupiter's gravitational influence had stopped a planet from forming in the first place, rather than destroying one that had already formed. These computer models allowed scientists to run the clock backward, simulating how the early solar system might have evolved under different conditions. When they included Jupiter's migration in their simulations, the models successfully reproduced many of the observed features of the modern asteroid belt. The low total mass, the excited orbital dynamics, the compositional mixing between inner and outer solar system materials, all of these characteristics emerged naturally from models that included giant planet migration. The evidence supporting these formation models comes from multiple sources, each providing a different piece of the puzzle. Meteorites that fall to Earth carry with them the chemical signatures of their parent bodies, allowing us to study asteroid compositions in exquisite detail. The isotopic ratios preserved in these space rocks tell us about the temperature and chemical conditions that existed when their parent asteroids formed. Some meteorites show clear evidence of having formed in a water-rich environment, with minerals that could only have crystallized in the presence of liquid water. These objects must have originated from parent bodies that contained substantial amounts of ice, indicating formation in the cold outer regions of the solar system. Other meteorites preserve the signatures of high-temperature processing, suggesting formation closer to the Sun, where temperatures were sufficient to vaporize volatile materials. The mixing of these different meteorite types provides strong evidence for the large-scale redistribution of materials that characterizes the Grand Tack model. Without some mechanism to transport objects between different regions of the solar system, we wouldn't expect to find such diverse compositions represented in the asteroid belt. Space missions have revolutionized our understanding of individual asteroids and their formation histories. The Dawn mission's detailed exploration of Vesta revealed a world that had experienced a complex geological evolution despite its small size. Vesta's surface shows evidence of extensive volcanism, impact cratering, and even the presence of organic compounds that may have been delivered by impacting asteroids from the outer solar system. The discovery of water ice on Ceres was particularly surprising. This dwarf planet, located in the relatively warm inner portions of the asteroid belt, shouldn't have been able to retain water ice on its surface. Yet Dawn's observations revealed bright spots in crater floors that appear to be deposits of nearly pure water ice, along with evidence for a subsurface ocean that may still exist today. These discoveries support the idea that Ceres formed much farther from the Sun, in the cold outer regions where water ice could condense and be incorporated into growing planetesimals. Its current location in the asteroid belt represents the end result of a long journey inward, carried by the gravitational currents generated by Jupiter's migration. The study of asteroid families provides another window into belt formation and evolution. These families are groups of asteroids that share similar orbital characteristics and compositions, suggesting they originated from the breakup of larger parent bodies. By studying the size distributions and orbital properties of family members, scientists can reconstruct the collisional history of the belt and estimate how much material has been lost over time. Some asteroid families are relatively young, formed by collisions that occurred within the last few million years. Others are ancient, with ages approaching the solar system's formation. The existence of these old families tells us that large asteroids were being disrupted by collisions very early in solar system history, consistent with models that predict high collision velocities in the primordial belt. The ongoing collisional evolution of the asteroid belt continues to shape its population today. High-velocity impacts between asteroids create new fragments, while grinding existing objects down to smaller sizes. This process operates like a cosmic mill, slowly reducing the average size of belt objects over billions of years. Observations with the Hubble Space Telescope have even captured some of these collisional events in action. In several cases, astronomers have observed asteroids that appear to be slowly disintegrating, shedding material in comet-like tails, despite being too far from the Sun for ice sublimation to be responsible. These observations suggest that some asteroids are so weakly bound that even small perturbations can cause them to break apart. The role of rotational forces in asteroid evolution adds yet another layer of complexity to the story. As asteroids are struck by smaller fragments or experience gravitational torques from planetary encounters, their rotation rates can change. Some asteroids spin up to the point where centrifugal forces overcome their weak gravitational self-attraction, causing them to shed material or break apart entirely. This rotational breakup process may be responsible for creating some of the binary and multiple asteroid systems that have been discovered through ground-based and spacecraft observations. These systems, where two or more asteroids orbit around their common center of mass, provide valuable information about asteroid internal structure and formation processes. The study of asteroid colors and spectra has revealed subtle but important clues about their formation and evolution. Asteroids that have experienced significant collisional processing tend to have different spectral properties than those that have remained relatively intact since formation. By mapping these spectral variations across the belt, scientists can identify regions where collisional evolution has been particularly intense. Some of the most primitive asteroids, those that have changed least since formation, are found in the outer portions of the main belt and in certain dynamically stable regions called Trojan zones. These objects preserve nearly pristine records of the conditions that existed in the early solar system, making them prime targets for future sample return missions. The connection between asteroids and comets has become increasingly apparent as our understanding of both populations has improved. Many asteroids, particularly those in the outer belt, show spectroscopic evidence for hydrated minerals and organic compounds that are more commonly associated with comets. Some objects even display comet-like activity when they approach the Sun, developing tails of gas and dust despite being located within the traditional asteroid belt. This blurring of the boundary between asteroids and comets supports formation models that involve large-scale mixing of materials from different regions of the solar system. Objects that formed as comets in the outer solar system could have been scattered inward to asteroid-like orbits, while objects that formed as asteroids could have been scattered outward to comet-like orbits. The study of asteroid belt formation has implications that extend far beyond our own solar system. As astronomers discover more and more exoplanetary systems, they find that many of these systems have experienced dramatic evolutionary histories involving planetary migration. Understanding how migration affects the formation and evolution of debris belts helps us interpret observations of dust disks around other stars. Some exoplanetary systems show evidence for multiple debris belts at different distances from their host stars, suggesting complex migration histories involving multiple giant planets. Others show signs of recent collisional activity, with warm dust that must be continuously replenished by ongoing asteroid collisions. The asteroid belt also serves as a natural laboratory for studying processes that operated throughout the early solar system. The size distributions, compositional gradients, and dynamical structures observed in the belt provide templates for understanding how similar processes might have operated in the regions where the terrestrial planets formed. Recent theoretical work has suggested that the terrestrial planet region may have experienced its own version of the collisional evolution that characterizes the asteroid belt. During the final stages of terrestrial planet formation, when Mars-sized planetary embryos were colliding to form the final planets, the region between the orbits of the growing worlds may have been filled with debris not unlike what we see in the asteroid belt today. The late heavy bombardment, a period of intense cratering that affected the inner solar system around 4 billion years ago, may represent the final stages of this collisional evolution. During this period, the remaining planetesimals and debris from terrestrial planet formation were gradually cleared out by gravitational interactions with the newly formed planets. The asteroid belt provides a window into this violent period of solar system history. Many of the largest asteroids show evidence for ancient impact basins that may have formed during the late heavy bombardment. By studying these ancient scars, scientists can piece together the conditions that existed during this crucial period in solar system evolution. As we continue to explore the asteroid belt with increasingly sophisticated instruments and theoretical models, new puzzles and discoveries continue to emerge. Recent observations have revealed unexpected compositional variations within individual asteroid families, suggesting that even the parent bodies of these families had complex internal structures and formation histories. The discovery of asteroid moons has provided new insights into the internal structure and formation of these small worlds. Many asteroid moons appear to have formed through collisional processes, where impacts excavated material that was then gravitationally captured to form satellite systems. Some of the largest asteroids show evidence for differentiated internal structures. with metallic cores surrounded by rocky mantles. These objects represent failed planets, worlds that began the process of planetary differentiation, but were prevented from completing it by the disruptive influence of Jupiter's gravity. The study of these differentiated asteroids provides unique insights into the earlier stages of planetary formation. Unlike the terrestrial planets, which have been heavily modified by billions of years of geological activity, differentiated asteroids preserve nearly pristine records of the conditions that existed during the first few million years of solar system history. Understanding asteroid belt formation has also proven crucial for assessing the impact hazard that these objects pose to Earth. The processes that scattered asteroids from the belt into Earth-crossing orbits operate on timescales of millions to billions of years, but they continue to operate today. By understanding how the belt formed and evolved, scientists can better predict how it will continue to evolve in the future. The asteroid belt represents one of the most successful case studies in planetary science, where detailed observations, sophisticated computer modeling, and theoretical insights have combined to create a comprehensive understanding of a complex astronomical phenomenon. Yet even with all we've learned, new discoveries continue to surprise us and refine our understanding of how this remarkable region of our solar system came to exist. As we prepare to delve even deeper into the specific mechanisms and evidence that have shaped our understanding of asteroid belt formation, remember that you're witnessing the unfolding of one of astronomy's greatest detective stories. Each meteorite that falls to Earth, each spacecraft observation, each computer simulation adds another piece to this cosmic puzzle, bringing us closer to a complete understanding of how worlds are born, how they evolve, and how the gravitational architecture of planetary systems shapes the distribution of matter across billions of years of cosmic time. The evidence for these complex formation scenarios comes from some of the most sophisticated detective work in all of science. Every meteorite that falls to Earth carries within its crystalline structure a story written in isotopes and minerals, a chemical fingerprint that reveals where and when its parent asteroid formed. These space rocks are like cosmic time capsules, preserving conditions from the earliest epochs of solar system history in ways that no terrestrial rock ever could. When scientists first began analyzing meteorites in detail, they expected to find a relatively uniform collection of materials reflecting the average composition of the solar nebula. Instead, they discovered something far more intriguing. The meteorites showed dramatic variations in their isotopic compositions, variations that could only be explained if their parent bodies had formed under vastly different conditions and at different locations throughout the solar system. Some meteorites contain minerals that could only have crystallized in the presence of liquid water, indicating formation within asteroids that once harbored subsurface oceans. Others preserve the signatures of extreme heating, with mineral assemblages that require temperatures approaching those found in planetary interiors. Still others show evidence of rapid cooling from high temperatures, suggesting formation in the aftermath of catastrophic collisions that briefly melted entire asteroids. Perhaps most remarkably, some meteorites contain microscopic grains that predate the formation of our solar system entirely. These pre-solar grains, identified by their exotic isotopic compositions, formed in the atmospheres of dying stars and were incorporated into the growing asteroids during the earliest stages of solar system formation. They represent literal stardust, remnants of stellar nucleosynthesis, that somehow survived the violent processes of planetary accretion. The distribution of these different meteorite types provides crucial evidence for the large-scale mixing processes that shaped asteroid belt formation. If the belt had formed from materials that originated entirely within its current boundaries, we would expect to see a relatively narrow range of compositions reflecting the local conditions in that region. Instead, we observe a bewildering diversity that can only be explained by the transport of materials from across the solar system. The timing constraints provided by meteorite studies have proven equally revealing. By measuring the decay products of short-lived radioactive isotopes, scientists can determine when different meteorite parent bodies formed and differentiated. These measurements consistently point to formation timescales of just a few million years, far shorter than the 100-million-year timescales once thought necessary for planetary assembly. This rapid formation timeline has profound implications for understanding asteroid belt evolution. It means that the largest asteroids had already formed and begun to differentiate before Jupiter reached its full size and began its dramatic migration. The disruption of the belt therefore involved the breakup of already formed worlds, rather than the prevention of initial accretion. The study of asteroid families has provided another crucial line of evidence for understanding belt formation and evolution. These families represent groups of asteroids with similar orbital characteristics and spectroscopic properties, suggesting they originated from the breakup of common parent bodies. By analyzing the size distributions and velocity dispersions of family members, scientists can reconstruct the energetics of the collisions that created them. Some of the largest asteroid families appear to be extremely ancient, with ages approaching the formation age of the solar system itself. The very existence of these old families tells us that violent collisions were occurring in the asteroid belt almost from the very beginning, consistent with models that predict early gravitational stirring by Jupiter's formation and migration. The Vesta family provides perhaps the most detailed example of how these collisional studies work. Spectroscopic observations reveal that hundreds of smaller asteroids share the distinctive basaltic composition of Vesta itself, indicating they are fragments blasted from the larger asteroid's surface by ancient impacts. The Dawn spacecraft's detailed mapping of Vesta's surface revealed enormous impact basins that are almost certainly the source craters for these fragments. What makes the Vesta family particularly interesting is that some of its fragments have made their way to Earth as meteorites. The HED meteorites, standing for Howardite, Eucrite, and Diogenite, have been definitively linked to Vesta through detailed spectroscopic matching. This connection allows scientists to study samples of Vesta in terrestrial laboratories, analyzing their mineral compositions, crystallization ages, and cooling histories with a precision impossible to achieve through remote sensing alone. The story told by these Vesta meteorites is one of rapid differentiation and complex thermal evolution. The Eucrites are basaltic rocks that crystallized from magma oceans on Vesta's surface, while the Diogenites represent deeper crustal materials that cooled more slowly within the asteroid's interior. The Howardites are impact breccias, mixtures of surface materials welded together by the shock and heat of collisions. Cooling rate studies of these meteorites reveal that Vesta's interior remained partially molten for tens of millions of years after its initial formation, heated by the decay of aluminum-26 and other short-lived radioactive isotopes. This extended period of internal activity allowed the asteroid to develop a complex internal structure with a metallic core, ultramafic mantle, and basaltic crust, making it essentially a miniature planet frozen in time. The preservation of this complex structure tells us something important about the timing of asteroid belt disruption. If Jupiter's gravitational stirring had begun immediately after Vesta's formation, the increased collision velocities would have shattered the asteroid before it could complete its differentiation. The fact that Vesta survived largely intact suggests that the most disruptive phase of belt evolution occurred somewhat later, after the largest asteroids had already formed and differentiated. Computer simulations of asteroid belt evolution have become increasingly sophisticated, incorporating not just gravitational dynamics, but also the complex physics of collisional outcomes. These models reveal that the transition from accretional growth to collisional erosion is not a simple binary switch, but rather a complex process that depends on the size distribution of objects, their internal structures, and the velocity distribution of collisions. In the early phases of belt evolution, when collision velocities were still relatively low, impacts between asteroids could lead to complex outcomes. Small objects might stick to larger ones, contributing to continued growth. Medium-sized impacts might excavate material from asteroid surfaces without completely disrupting the target, creating the complex crater histories we observe on asteroids today. Only the most energetic collisions would completely shatter their targets, creating the debris that we see in modern asteroid families. As Jupiter's gravitational influence increased collision velocities throughout the belt, the balance gradually shifted from growth to erosion. The critical velocity threshold above which collisions become destructive rather than constructive depends on the target's size, composition, and internal structure. For typical stony asteroids, a few kilometers in diameter, this threshold lies somewhere around a few hundred meters per second. Once collision velocities exceeded this critical threshold throughout most of the belt, the asteroid population entered a phase of gradual grinding down that continues today. Large asteroids are broken apart into smaller fragments, which are themselves broken apart into still smaller pieces. This collisional cascade operates like a cosmic mill, slowly reducing the average size of belt objects over geological time. The efficiency of this grinding process depends sensitively on the impact strength of the target materials. Solid, coherent rock can withstand much higher impact energies than loose, fractured material. Many asteroids appear to be what scientists call rubble piles, loose collections of fragments held together primarily by their own weak gravity rather than by material strength. These rubble pile structures may actually represent an adaptation to the high-velocity collision environment of the modern asteroid belt. When a solid asteroid is hit by a high-speed projectile, the impact can completely shatter the entire object. But when a rubble pile asteroid is hit, the impact energy can be absorbed and dissipated through the rearrangement of fragments, allowing the overall structure to survive impacts that would destroy a solid object. The discovery of binary and multiple asteroid systems has provided new insights into these collisional processes. Many asteroid binaries appear to have formed through the fission of rapidly rotating parent bodies, where centrifugal forces overcame the weak gravitational binding, holding loose fragments together. Others may have formed through gravitational capture of debris created during energetic collisions. The orbital dynamics of these asteroid systems provide unique laboratories for studying the internal structure and composition of their component objects. By measuring the orbital periods and separations of binary asteroids, scientists can determine their masses and bulk densities, revealing whether they are solid objects or loose rubble piles. Some of the most surprising discoveries have come from radar observations of near-Earth asteroids that originated in the main belt. These studies have revealed that many asteroids have bulk densities significantly lower than their constituent materials, confirming that they must have substantial internal void space consistent with rubble pile structures. The thermal evolution of asteroids provides another window into their formation and subsequent history. Objects that formed early in solar system history, when aluminum-26 was still abundant, experienced significant internal heating that could drive differentiation and even partial melting. Later forming objects, or those that formed from materials that had already been processed by earlier heating events, remained largely unmodified by thermal processing. This thermal evolution history is preserved in the mineralogy and petrology of meteorites. Primitive meteorites, like carbonaceous chondrites, show little evidence of thermal processing, preserving nearly pristine records of nebular condensation and accretion processes. In contrast, differentiated meteorites, like the HED suite from Vesta, show clear evidence of high-temperature processing and chemical differentiation. The transition between these two extremes is preserved in meteorites from asteroids that experienced intermediate levels of thermal processing. These objects, represented by meteorite types like the ordinary chondrites, show evidence of heating sufficient to mobilize volatile elements and recrystallize mineral structures without achieving full differentiation. The distribution of these different thermal processing signatures among meteorites provides constraints on the size distribution and formation timescales of their parent asteroids. Objects larger than a few hundred kilometers in diameter would have experienced significant internal heating, regardless of when they formed, while smaller objects would have remained largely unprocessed unless they formed very early when aluminum-26 concentrations were at their peak. The discovery of organic compounds in certain types of meteorites has opened new avenues for understanding asteroid formation and evolution. These organic materials, including amino acids and other complex molecules, appear to have formed through aqueous alteration processes within their parent asteroids. The presence of liquid water within asteroids, sustained by radioactive heating and insulated by overlying rock, created environments where complex chemistry could occur over millions of years. These findings have profound implications for understanding the role of asteroids in delivering organic materials to the early Earth. If asteroids were sites of active organic chemistry during the first few tens of millions of years of solar system history, they could have served as factories for producing the molecular building blocks of life before delivering them to planetary surfaces through impact processes. The water content of asteroids represents another crucial piece of the formation puzzle. Spectroscopic observations reveal that many asteroids, particularly those in the outer portions of the belt, contain significant amounts of water locked in hydrated minerals. This water could only have been incorporated if these objects formed beyond the snowline, where water ice could condense in the cooling solar nebula. The presence of hydrated asteroids throughout the belt, including regions that are currently too warm for water ice to be stable, provides strong evidence for the large-scale radial transport of materials that characterizes the Grand Tack and similar migration models. These water-bearing objects must have formed in the cold outer regions of the solar system before being scattered inward to their current locations. Recent spacecraft observations have revealed that even some of the driest-looking asteroids contain trace amounts of water, either locked in mineral structures or existing as ice deposits in permanently shadowed regions. The Hayabusa 2 mission study of asteroid Ryugu, for example, found evidence for hydrated minerals despite the object's location in the warm inner portions of the belt. The isotopic composition of water in asteroids provides additional clues about their formation locations and histories. Water that condensed at different distances from the Sun or at different times in solar system history should have subtly different isotopic signatures. By comparing these signatures between different asteroid types and with water in the Earth's oceans, scientists can trace the sources and transport pathways of water throughout the early solar system. These studies have revealed that asteroid water shows a range of isotopic compositions, some similar to terrestrial water and others distinctly different. This diversity suggests that asteroids incorporated water from multiple sources, possibly including both solar nebula condensates and water ice inherited from the interstellar medium that preceded solar system formation. The magnetic properties of meteorites have provided yet another tool for understanding asteroid formation and evolution. Many meteorites preserve records of ancient magnetic fields, either from the solar nebula or from magnetic dynamos operating within their parent asteroids. These paleomagnetic signatures can reveal information about the timing and intensity of magnetic field exposure, providing constraints on formation locations and thermal histories. Some differentiated asteroids appear to have maintained active magnetic dynamos for tens of millions of years, powered by core crystallization processes similar to those operating in terrestrial planets. The preservation of these magnetic signatures in meteorites tells us that some asteroids achieved planetary-like internal structures before being disrupted by collisional processes. The study of noble gases trapped within meteorites has revealed information about the solar wind and cosmic ray exposure histories of their parent asteroids. These measurements can distinguish between materials that were exposed at asteroid surfaces versus those that were buried in interiors, providing constraints on the collisional histories and regolith development processes operating on different asteroids. Cosmic ray exposure ages, determined from the buildup of cosmogenic nuclides in meteorites, reveal the timescales over which asteroid fragments have been traveling through space after being ejected from their parent bodies. These measurements show that most meteorites have been in space for millions to tens of millions of years, indicating that the collisional processes responsible for their ejection operate continuously over geological time. The delivery mechanisms that transport meteorites from the asteroid belt to Earth provide insights into the dynamical evolution of the belt itself. Most meteorites appear to reach Earth through gravitational resonances with Jupiter that can gradually pump up the eccentricities of asteroid orbits until they become Earth-crossing. These same resonances that deliver meteorites to Earth also contribute to the ongoing depletion of the asteroid belt over solar system history. The rate at which meteorites fall to Earth, combined with estimates of the fraction of belt asteroids that eventually become Earth crossers, allows scientists to estimate the rate at which the belt is losing mass through these dynamical processes. These calculations suggest that the belt continues to lose material at a slow but steady rate, with a half-life of hundreds of millions to billions of years. This ongoing mass loss means that the asteroid belt was somewhat more massive in the past than it is today. though still far less massive than the original population of planetesimals that formed in the region. The cumulative effect of billions of years of collisional grinding and dynamical depletion has reduced the belt to its current skeletal state. Despite this ongoing evolution, the asteroid belt maintains a remarkably stable overall structure. The major compositional zones, orbital resonances, and size distributions have remained relatively unchanged for billions of years. This stability reflects a kind of dynamical equilibrium, where ongoing loss processes are balanced by the finite supply of source material and the protection provided by gravitational resonances and dynamical barriers. As we continue our exploration of asteroid belt formation and evolution, we begin to see how this seemingly simple collection of space debris actually represents one of the most complex and fascinating regions of our solar system. Every observation, every meteorite analysis, every computer simulation adds new layers of understanding to a story that connects the smallest grains of cosmic dust to the largest planets, weaving together themes of formation, destruction, migration, and survival that have shaped our solar system's architecture over 4.5 billion years of cosmic evolution. The mechanisms that drove this cosmic reshuffling operate on scales both vast and intimate, from the gentle whisper of gas drag acting on microscopic particles to the thunderous gravitational resonances that can fling entire worlds across the solar system. To understand how the asteroid belt came to exist in its current form, we need to appreciate the delicate interplay between these forces, each operating on its own timescale, each contributing its own verse to the grand symphony of planetary formation. Picture the early solar system as a vast construction site, filled with the raw materials for world building but lacking any central coordination. Gravity provides the blueprints, but the actual assembly process depends on countless chance encounters between objects ranging in size from dust grains to mountain-sized boulders. In most regions of the solar system, this chaotic construction process eventually organized itself into the orderly arrangement of planets we see today. But in the asteroid belt region, something went fundamentally wrong with the construction project. The streaming instability that we touched on earlier represents one of the most elegant solutions to what planetary scientists call the meter barrier problem. Imagine trying to build a sandcastle where every grain of sand repels every other grain. That's essentially the challenge faced by growing planetesimals in the early solar system. Individual particles can stick together through weak electrostatic forces, but as they grow larger, these forces become insufficient to hold them together against the turbulent motions of the surrounding gas. The streaming instability bypasses this problem through a kind of cosmic choreography. When solid particles drift through the gaseous disk, they create pressure waves in the surrounding gas, much like a school of fish swimming through water. These pressure variations, in turn, influence the motion of other nearby particles, creating feedback loops that can concentrate solids into dense filaments that stretch across vast distances. These filaments become so dense that gravity finally takes control, causing them to fragment into gravitationally bound clumps that become the first generation of planetesimals. It's a process that operates almost like magic, transforming a smooth distribution of particles into a lumpy collection of solid objects through nothing more than the complex interplay of gas dynamics and gravitational physics. In the asteroid belt region, this process initially worked exactly as it should have. Computer simulations suggest that streaming instabilities operating in the early solar nebula could have produced thousands of planetesimals in the belt region, ranging in size from a few kilometers to hundreds of kilometers in diameter. These objects would have followed relatively circular orbits and collided with each other at gentle velocities that promoted growth rather than destruction. But the streaming instability is just the beginning of the story. Once planetesimals form, they begin a complex dance of growth through gravitational attraction and collision. In the inner solar system, where collision velocities remained low, this dance led to the formation of planetary embryos and eventually the terrestrial planets. In the outer solar system, beyond the orbit of Jupiter, it led to the formation of the cores of the giant planets. The asteroid belt region should have followed a similar path. The raw materials were there. The initial planetesimal formation process operated normally, and the orbital dynamics initially favored continued growth. But as Jupiter grew to maturity, its gravitational influence began to reach across the solar system like invisible fingers, stirring up the orbital motions of objects throughout the belt region. This gravitational stirring didn't happen overnight. It was a gradual process that unfolded over millions of years, slowly but inexorably changing the character of collisions in the belt from constructive to destructive. As orbital eccentricities and inclinations increased under Jupiter's influence, the gentle bump-and-stick collisions that had been building larger worlds gave way to violent smash-ups that shattered existing objects into fragments. The physics of this transition involve what scientists call the fragmentation threshold, a critical collision velocity above which impacts become destructive rather than constructive. For typical rocky materials, this threshold lies somewhere around a few hundred meters per second. Below this speed, collisions tend to result in accretion, as the kinetic energy of impact can be absorbed through deformation and heating. Above this speed, the impact energy exceeds the gravitational binding energy of the target, leading to catastrophic disruption. Jupiter's gravitational stirring pushed collision velocities in the asteroid belt well above this critical threshold, effectively switching off planet formation and beginning a process of collisional evolution that continues today. Large planetesimals that had been growing steadily for millions of years suddenly found themselves in an environment where every encounter with another object posed a threat to their continued existence. The largest objects, those with the strongest gravitational binding, were the most likely to survive this transition. This is why we still see objects like Ceres and Vesta in the belt today, massive enough to hold themselves together even in the face of devastating impacts. But smaller objects faced a constant grinding process, being broken apart and reformed in an endless cycle of destruction and reaccumulation. The Grand Tack migration model adds another layer of complexity to this story. Rather than simply stirring up the belt from Jupiter's current location, this model proposes that the giant planet actually migrated through the belt region, passing close enough to scatter planetesimals in all directions. This close encounter would have been catastrophic for any objects trying to form in the belt, not just stirring up their orbits, but actually ejecting most of them from the region entirely. The migration wasn't a simple inward journey followed by an outward return. Computer simulations suggest it was a complex process, driven by interactions between Jupiter and the gaseous disk from which it formed. As Jupiter grew, it opened up gaps in the disk, creating pressure variations that exerted torques on the planet's orbit. These disk-planet interactions caused Jupiter to spiral inward, moving from its initial formation location at about 3.5 astronomical units to as close as 1.5 astronomical units from the Sun. This inward migration brought Jupiter uncomfortably close to the orbits of the forming terrestrial planets, potentially disrupting their formation as well. But as Saturn grew to maturity, it began to feel similar torques from the disk. When Saturn's orbital period became resonantly coupled to Jupiter's, the two planets began to migrate outward together, eventually settling into orbits similar to their current positions. The effects of this migration on the asteroid belt were profound and long-lasting. During Jupiter's inward journey, it encountered planetesimals that had formed in the belt region and scattered them in all directions. Some were flung into the inner solar system, where they may have contributed to the formation of the terrestrial planets or the late heavy bombardment that scarred the surfaces of the Moon and other inner solar system bodies. During Jupiter's outward migration, it encountered a different population of objects, primitive planetesimals that had formed in the cold outer regions of the solar system. Some of these objects were scattered inward, finding stable orbital niches in what we now call the asteroid belt. This explains the compositional diversity we observe in the belt today, with dry, rocky objects dominating the inner regions and water-rich, carbon-bearing objects more common in the outer parts. The mixing process, created by Jupiter's migration, was so thorough that the modern asteroid belt contains objects from across the solar system. It's like a cosmic refugee camp, populated by survivors from many different regions, each carrying with them the chemical signatures of their birthplaces. This mixing has proven invaluable for understanding the conditions that existed in different parts of the early solar nebula. Recent research has revealed that this migration scenario can explain not just the structure of the asteroid belt, but many other puzzling features of our solar system as well. The small size of Mars, for example, can be understood as a consequence of Jupiter's inward migration, which scattered away much of the material that should have been available for Mars to incorporate during its formation. The compositional differences between the terrestrial planets also find natural explanations in the grand Tack model. Earth and Venus, which formed closer to the Sun, incorporated mostly dry, rocky materials, but Mars, which formed farther out, should have had access to more water-rich materials from the outer solar system. The fact that Mars appears to be relatively dry suggests that much of this water-rich material was scattered away during Jupiter's migration. Even the delivery of water to Earth may be connected to Jupiter's migration. As the giant planet moved inward and then outward, it scattered water-rich planetesimals throughout the inner solar system. Some of these objects may have been captured by the growing terrestrial planets, delivering the water that eventually filled Earth's oceans and made our world habitable. The timing of Jupiter's migration provides crucial constraints on the formation timeline of the inner solar system. If the migration occurred too early, it would have prevented the terrestrial planets from forming at all. If it occurred too late, it wouldn't have been able to scatter away the material that was supposed to form a planet in the asteroid belt region. Meteorite studies suggest that the migration must have occurred within the first few million years of solar system formation, while the gaseous disk was still present to drive the migration process. This timing is consistent with evidence from differentiated asteroids like Vesta, which show that large planetesimals had already formed and begun to differentiate before Jupiter's gravitational influence became dominant. The alternative Jupiter-Saturn chaotic excitation model proposes a somewhat different mechanism for achieving similar results. In this scenario, Jupiter and Saturn don't necessarily migrate large distances, but their orbits evolve into a near-resonant configuration that generates chaotic dynamics throughout the asteroid belt region. Chaos in this context doesn't mean random motion, but rather motion that is extremely sensitive to initial conditions. Small changes in an object's orbit can lead to dramatically different evolutionary pathways, with some objects being scattered out of the belt, while others find stable orbital niches where they can survive for billions of years. The chaotic excitation model can reproduce many of the observed features of the asteroid belt without requiring the large-scale planetary migration invoked by the grand Tack scenario. It provides an alternative explanation for the belt's low mass, excited orbital dynamics, and compositional mixing, demonstrating that multiple formation pathways might be capable of producing similar final states. The empty primordial belt model takes an even more radical approach, suggesting that very few planetesimals ever formed in the asteroid belt region to begin with. According to this model, the belt we observe today was populated entirely by objects scattered from other regions during terrestrial planet formation and giant planet evolution. This model draws support from detailed studies of asteroid orbital dynamics and compositions. The evidence suggests that different types of asteroids were implanted from different source regions at different times, creating the complex population we observe today. The S-type asteroids that dominate the inner belt appear to have been scattered outward from the terrestrial planet formation region, while the C-type asteroids in the outer belt were implanted from beyond Jupiter's orbit. If this model is correct, it would mean that the asteroid belt region was essentially empty during the primary phase of planetary formation, with its current population representing cosmic debris that was swept up later during the final stages of solar system evolution. This would make the belt less of a failed planet and more of a cosmic junkyard, filled with the leftover remnants of planetary formation processes that operated elsewhere. The debate between these different formation models continues to drive new research and observations. Each model makes specific predictions about the properties of asteroids and the structure of the belt that can be tested through increasingly sophisticated observations and computer simulations. Space missions like Dawn, which explored both Vesta and Ceres in unprecedented detail, have provided crucial data for discriminating between these models. The complex geology revealed on both objects supports the idea that large asteroids formed early and experienced significant thermal evolution before the belt was dynamically excited by Jupiter's influence. The discovery of organic compounds on Ceres, for example, suggests that this dwarf planet formed in the cold outer solar system, where such materials could condense, supporting models that invoke large-scale radial mixing of materials. Similarly, the preservation of Vesta's differentiated structure indicates that it formed and evolved before collision velocities in the belt became high enough to disrupt large objects. Future missions to other asteroids will continue to refine our understanding of belt formation. The OSIRIS-REx mission's study of asteroid Bennu and Japan's Hayabusa 2 mission to asteroid Ryugu have already revealed new details about the structure and composition of these primitive objects. providing insights into the processes that operated during the earliest phases of solar system evolution. Ground-based observations continue to contribute important pieces of the puzzle as well. Large-scale surveys like the Catalina Sky Survey and Linear have catalogued hundreds of thousands of asteroids, revealing statistical properties of the belt population that constrain formation models. Spectroscopic studies have mapped the compositional structure of the belt in ever greater detail, revealing subtle variations that reflect the complex mixing processes that shaped its formation. The study of asteroid families, groups of objects with similar orbits and compositions that originated from the breakup of common parent bodies, provides another powerful tool for understanding belt evolution. By analyzing the age distribution of these families, scientists can reconstruct the collisional history of the belt and estimate how its population has changed over time. Some families are extremely young, formed by collisions within the last few million years, that we can sometimes observe directly through ground-based telescopes. Others are ancient, with ages approaching the formation age of the solar system itself. The existence of these old families tells us that violent collisions have been shaping the belt's population almost from the very beginning. The size distribution of objects within these families provides insights into the physics of catastrophic collisions. When a large asteroid is shattered by an impact, the fragments follow specific mathematical relationships that depend on the target's internal structure and the energy of the collision. By comparing observed size distributions with theoretical predictions, scientists can infer the internal properties of asteroids and the energetics of the collisions that destroyed them. The ongoing collisional evolution of the asteroid belt continues to shape its population today. High-velocity impacts between asteroids create new fragments while grinding existing objects down to smaller sizes. This process operates like a cosmic mill, slowly reducing the average size of belt objects over billions of years, while occasionally creating spectacular disruption events that produce new families of fragments. Recent observations have captured some of these disruption events in real time. The Hubble Space Telescope observed asteroid P/2013 R3 slowly disintegrating into multiple fragments, providing direct evidence for the ongoing collisional processing that shapes the belt's evolution. Similarly, ground-based surveys have detected numerous asteroids with comet-like tails, apparently shedding material as they slowly spin apart under rotational stresses. These observations remind us that the asteroid belt is not a static collection of ancient debris, but a dynamic environment where new objects are constantly being created through the breakup of larger parents. The belt we observe today is the product of billions of years of collisional evolution, and it will continue to evolve as long as asteroids continue to collide with each other. The thermal evolution of asteroids adds another dimension to their formation story. Objects that formed early in solar system history when short-lived radioactive isotopes like aluminum-26 were still abundant, experienced significant internal heating that could drive differentiation and create complex internal structures. Later forming objects, or those that incorporated materials that had already been processed by earlier heating events, remained relatively primitive. This thermal processing created the diverse range of meteorite types that we study in terrestrial laboratories. Primitive meteorites like carbonaceous chondrites preserve nearly pristine records of nebular processes, while differentiated meteorites from asteroids like Vesta show clear evidence of high-temperature processing and chemical fractionation. The transition between these extremes is preserved in meteorites that experienced intermediate levels of thermal processing. These objects show evidence of heating sufficient to mobilize volatile elements and recrystallize mineral structures without achieving full differentiation, providing insights into the thermal conditions that existed within asteroids of different sizes and formation times. The preservation of water and organic compounds in some asteroids indicates that not all objects experience severe thermal processing. These primitive bodies serve as repositories of materials that formed under the cold conditions of the outer solar nebula, carrying within their structures the chemical signatures of processes that operated billions of years ago in regions far from the Sun. The isotopic compositions of these materials provide powerful tools for understanding the formation environment of their parent asteroids. Different isotopic ratios can reveal information about temperature, pressure, and chemical conditions during formation, as well as the sources of the materials that were incorporated into growing planetesimals. Some isotopic signatures point to inheritance from the interstellar medium that preceded solar system formation, while others reflect processing within the solar nebula itself. By mapping these isotopic variations across different asteroid types and different regions of the belt, scientists can reconstruct the complex history of material transport and processing that shaped the early solar system. The magnetic properties preserved in some meteorites provide additional clues about asteroid formation and early solar system conditions. Some objects appear to have been magnetized by strong magnetic fields, either from the solar nebula or from magnetic dynamos operating within their parent bodies. These paleomagnetic signatures can reveal information about the intensity and duration of magnetic field exposure, providing constraints on formation environments and thermal histories. The noble gas compositions of meteorites tell yet another part of the story, revealing information about exposure to solar wind particles and cosmic rays during their journey from asteroid to Earth. These measurements can distinguish between materials that were exposed at asteroid surfaces versus those that were buried in interiors, providing insights into the regolith development and impact gardening processes that operate on asteroid surfaces. As we piece together all of these different lines of evidence, a picture emerges of asteroid belt formation as one of the most complex and fascinating chapters in the story of our solar system's evolution. It's a tale that connects the smallest dust grains to the largest planets, weaving together themes of formation, migration, collision, and survival that have shaped the distribution of matter throughout our cosmic neighborhood. The asteroid belt serves as both a graveyard of planetary dreams and a treasure trove of scientific information. In its scattered fragments, we can read the history of processes that operated throughout the early solar system, from the initial condensation of materials in the solar nebula to the final stages of terrestrial planet assembly. Every meteorite that falls to Earth carries with it a piece of this ancient story, a sample of materials that formed under conditions we can never directly observe, but can only infer through careful analysis and theoretical modeling. Each asteroid observed through ground-based telescopes or visited by spacecraft adds new chapters to our understanding of how planetary systems form and evolve. The ongoing exploration of the asteroid belt continues to reveal new surprises and refine our understanding of these ancient processes. As our observational capabilities improve and our theoretical models become more sophisticated, we gain deeper insights into the complex interplay of forces that shaped the early solar system and continue to govern its evolution today. But perhaps most importantly, the study of asteroid belt formation reminds us that our solar system is not a static arrangement of planets orbiting peacefully around the Sun, but rather the product of billions of years of dynamic evolution. The quiet emptiness between Mars and Jupiter hides a story of cosmic violence and planetary migration that fundamentally shape the world we call home, influencing everything from the size of Mars to the water content of Earth's oceans to the very possibility of life arising on our small blue planet floating in the vastness of space. As we venture deeper into this cosmic detective story, we encounter evidence that challenges our most fundamental assumptions about how worlds come to be. The asteroid belt, you see, represents something far more profound than a simple collection of space debris. It's a fossil record of cosmic catastrophe, a preserved moment in time when the delicate dance of planetary formation was violently interrupted by forces beyond imagination. Picture yourself as a cosmic archaeologist, carefully brushing away billions of years of dust to reveal the hidden layers of our solar system's tumultuous youth. Every fragment floating in that seemingly empty space between Mars and Jupiter tells a story, and when we piece these stories together, they reveal a narrative so dramatic it reads like science fiction, yet so precisely documented in stone and metal that we cannot doubt its truth. The chemical fingerprints preserved in meteorites that occasionally grace our planet, with their fiery arrival, speak of temperatures and pressures that existed when our sun was barely more than a glowing ember surrounded by a disk of cosmic dust. These space rocks carry within their crystalline structures the memories of a time when matter was learning how to become worlds, when the fundamental forces of gravity and electromagnetism were engaged in their eternal struggle to either build or destroy. But here's where the story becomes truly extraordinary. The asteroid belt we observe today is not the original population of objects that formed in that region. It's more like a cosmic refugee camp, populated by survivors from across the solar system who found themselves homeless after the Great Migration that reshaped our planetary neighborhood. Some of these refugees came from the warm inner regions where Earth and Venus were taking shape, carrying with them the dry, rocky compositions typical of worlds that formed close to the Sun. Others arrived from the cold outer reaches, beyond the orbit of Jupiter, bringing with them the icy, carbon-rich materials that could only condense in the frigid depths of space. These objects, dark as charcoal and rich in organic compounds, tell us stories of formation in regions so distant and cold that water could freeze solid and complex molecules could stick together without being torn apart by solar radiation. The mixing of these populations creates one of the most beautiful puzzles in planetary science. If you were to take a spectroscopic survey of the asteroid belt today, measuring the colors and compositions of thousands of objects, you would find a gradient that stretches from the inner edge to the outer boundary. Near Mars, the asteroids are mostly dry and rocky, similar to the material that makes up our own planet. But as you move outward toward Jupiter, you encounter increasing numbers of dark, primitive objects that clearly formed under very different conditions. This compositional gradient is like finding tropical fish swimming alongside Arctic seals, a clear indication that some powerful force has mixed up the natural order of things. That force was Jupiter's gravitational influence, operating over millions of years to scatter objects from their birthplaces and relocate them in new orbital homes across the solar system. The larger survivors in this cosmic diaspora tell individual tales of remarkable endurance. Ceres, now classified as a dwarf planet and comprising nearly a third of the belt's total mass, appears to have journeyed inward from the cold outer solar system. Its composition, rich in water ice and exotic salts, suggests it formed in the region between Jupiter and Saturn before being scattered to its current orbit through the complex gravitational choreography of planetary migration. Recent observations from the Dawn spacecraft revealed that Ceres harbors secrets that continue to surprise scientists. Bright spots on its surface, initially mysterious and puzzling, turned out to be deposits of nearly pure salt left behind by the sublimation of water ice. Even more remarkably, Ceres appears to have a subsurface ocean, a hidden sea that may have existed for billions of years beneath its rocky exterior. These discoveries transform our understanding of what it means to be an asteroid. Ceres isn't just a chunk of ancient rock, but a complex world with its own geology, its own history of internal evolution, and possibly even its own unique chemistry operating in the darkness beneath its surface. It's a reminder that even in the seemingly barren reaches of the asteroid belt, water finds a way to persist, to hide, to create environments where the unexpected might flourish. Vesta, the second largest asteroid, tells a different but equally compelling story. This battered world managed to achieve something remarkable during the early solar system's chaotic youth. It grew large enough and formed quickly enough to undergo the same kind of internal differentiation that created the terrestrial planets. Deep within Vesta's interior, temperatures rose high enough to melt rock, allowing heavy elements to sink toward the center, while lighter materials rose to the surface. The result was a miniature planet, complete with a metallic core, a rocky mantle, and a basaltic crust. Vesta became, in essence, a planetary embryo that was prevented from growing to full size by Jupiter's gravitational interference. Today, its heavily cratered surface bears the scars of billions of years of impacts, including enormous basins that are visible even through Earth-based telescopes. What makes Vesta's story particularly fascinating is that pieces of this ancient world have made their way to Earth as meteorites. The Dawn spacecraft's detailed mapping of Vesta's surface revealed impact craters that are almost certainly the source of these meteorite fragments. By studying these samples in terrestrial laboratories, scientists can analyze the internal structure and thermal history of an asteroid with a precision that would be impossible through remote observation alone. The meteorites from Vesta tell us that this small world remained partially molten for tens of millions of years after its formation, heated by the decay of radioactive elements that were much more abundant in the early solar system than they are today. This extended period of internal activity allowed Vesta to develop a complex layered structure that we can now study in exquisite detail through the analysis of its meteoritic fragments. But Vesta's survival as a differentiated world tells us something important about the timing of asteroid belt disruption. If Jupiter's gravitational stirring had begun immediately after Vesta's formation, the increased collision velocities would have shattered this small world before it could complete its internal evolution. The fact that Vesta survived largely intact suggests that the most disruptive phase of belt evolution occurred somewhat later, after the largest objects had already formed and achieved their internal structure. The evidence for this timing comes from multiple sources, each providing a different piece of the chronological puzzle. Radiometric dating of meteorites from differentiated asteroids consistently points to formation and differentiation timescales of just a few million years, far shorter than the hundreds of millions of years once thought necessary for planetary assembly. This rapid formation indicates that the disruption of the asteroid belt occurred after a substantial population of large planetesimals had already formed. The study of asteroid families provides another window into the belt's collisional history. These families represent groups of objects with similar orbital characteristics and compositions, suggesting they originated from the breakup of common parent bodies. By analyzing the size distributions and orbital properties of family members, scientists can reconstruct the energetics and timing of the collisions that created them. Some of the most ancient families appear to have formed very early in solar system history, indicating that violent collisions were occurring in the asteroid belt almost from the beginning. The survival of these old families, some with ages approaching 4 billion years, tells us that while the belt experienced intense collisional activity during its early evolution, it has achieved a kind of dynamical equilibrium that has allowed many structures to persist for enormous spans of time. The ongoing collisional evolution of the asteroid belt continues to shape its population today, but at a much slower pace than during the early period of intense bombardment. Modern collision velocities are high enough to fragment smaller objects, but generally insufficient to completely disrupt the largest asteroids. This creates a kind of size-dependent evolution, where small objects are continuously ground down while large objects remain relatively stable over geological time. Recent observations have captured some of these modern collisional events in real time. Ground-based telescopes and space-based observatories have detected asteroids in the process of disintegrating, slowly shedding material as they spin apart under rotational stresses or fragment under the accumulated damage of countless smaller impacts. These observations provide direct evidence for the ongoing processes that continue to reshape the belt's population. The thermal evolution that shaped the early asteroids created the diverse range of meteorite types that provide our most detailed information about conditions in the primordial solar system. Objects that formed when radioactive heating was at its peak experienced melting and differentiation, creating the iron meteorites that represent samples of asteroidal cores and the basaltic meteorites that form from surface lava flows on worlds like Vesta. But not all asteroids experience such intense heating. Smaller objects, or those that formed later when radioactive elements had already begun to decay, remained largely unprocessed. These primitive asteroids preserve nearly pristine records of the conditions that existed during the earliest phases of solar system formation, carrying within their structures materials that condense directly from the cooling solar nebula. The preservation of organic compounds in some of these primitive objects has opened new avenues for understanding the chemical complexity that existed in the early solar system. These organic materials, including amino acids and other complex molecules, appear to have formed through aqueous alteration processes within asteroid interiors, where liquid water sustained by radioactive heating created environments conducive to complex chemistry. These findings have profound implications for understanding the origins of life itself. If asteroids were sites of active organic synthesis during the first few tens of millions of years after solar system formation, they could have served as chemical factories, producing the molecular building blocks of life before delivering them to planetary surfaces through impact processes. The water content of asteroids represents another crucial aspect of their formation history. spectroscopic observations reveal that many asteroids, particularly those in the outer portions of the belt, contain significant amounts of water locked in hydrated mineral structures. This water could only have been incorporated if these objects formed beyond the snowline, where temperatures were low enough for water ice to condense and be accreted into growing planetesimals. The presence of hydrated asteroids throughout the belt, including regions that are currently too warm for water ice to be stable, provides compelling evidence for the large-scale radial transport of materials that characterizes planetary migration models. These water-bearing objects must have formed in the cold outer regions of the solar system before being scattered inward to their current locations by the gravitational influence of the migrating giant planets. The isotopic composition of water in asteroids provides additional clues about their formation locations and subsequent histories. Water that condensed at different distances from the Sun, or incorporated from different reservoirs in the early solar system, carries distinctive isotopic signatures that can be used to trace the sources and transport pathways of this most precious of molecules. Studies of these isotopic signatures have revealed that asteroid water shows a range of compositions, some similar to terrestrial water and others distinctly different. This diversity suggests that asteroids incorporated water from multiple sources, possibly including both materials that condensed from the solar nebula and pre-solar components that were inherited from the interstellar medium that preceded our solar system's formation. The magnetic properties preserved in some meteorites provide yet another tool for understanding asteroid formation and the conditions that existed in the early solar system. Some meteorites preserve records of ancient magnetic fields, either from the solar nebula itself or from magnetic dynamos that operated within their parent asteroids during the period of active differentiation. These paleomagnetic signatures can reveal information about the intensity and duration of magnetic field exposure, providing constraints on formation environments and thermal histories. Some differentiated asteroids appear to have maintained active magnetic dynamos for tens of millions of years, powered by the same kinds of core crystallization processes that generate magnetic fields in terrestrial planets today. The noble gas compositions of meteorites tell complementary stories about exposure to solar wind particles and cosmic rays during their long journey from asteroid belt to Earth. These measurements can distinguish between materials that were exposed at asteroid surfaces versus those that were buried in protected interiors, providing insights into the regolith development and space weathering processes that operate on airless bodies throughout the solar system. Cosmic ray exposure ages, determined from the buildup of cosmogenic nuclides produced by high-energy particle bombardment, reveal the timescales over which meteorite fragments have been traveling through space after being ejected from their parent asteroids. Most meteorites show exposure ages of millions to tens of millions of years, indicating that the collisional processes responsible for launching them on Earth-crossing trajectories operate continuously but relatively slowly over geological time. The delivery mechanisms that transport these samples from the asteroid belt to Earth provide insights into the dynamical processes that continue to shape the belt's evolution. Most meteorites appear to reach our planet through gravitational resonances with Jupiter that can gradually increase orbital eccentricities until formally belt-bound objects become Earth-crossers. These same resonances that deliver meteorites also contribute to the ongoing depletion of the asteroid belt over solar system history. Objects that wander into these resonant zones are slowly but inexorably removed from the belt, either ejected from the solar system entirely or delivered to the inner planets as meteorites or impact craters. The rate at which this process operates can be estimated from the meteorite flux to Earth, combined with models of the dynamical evolution of asteroid orbits. These calculations suggest that the asteroid belt continues to lose mass through resonant depletion, though at a rate much slower than the catastrophic depletion that occurred during its early evolution. This ongoing mass loss means that the belt was somewhat more massive in the past than it is today, though still far less massive than the original population of planetesimals that attempted to form in the region. The cumulative effect of billions of years of collisional grinding and dynamical depletion has reduced the belt to its current skeletal state, a pale shadow of what might have been a magnificent world. Yet despite this ongoing evolution, the asteroid belt maintains a remarkably stable overall structure. The major compositional zones, the locations of dynamical resonances, and the general size distribution of objects have remained relatively unchanged for billions of years. This stability reflects a kind of dynamical equilibrium, where ongoing loss processes are balanced by the finite supply of source material and the gravitational protection provided by stable orbital zones. As we continue to explore the asteroid belt through increasingly sophisticated ground-based observations and ambitious space missions, new discoveries continue to refine our understanding of its formation and evolution. Each new asteroid visited by spacecraft, each meteorite analyzed in terrestrial laboratories, each computer simulation of early solar system dynamics adds another piece to this cosmic puzzle. The story of asteroid belt formation ultimately reveals itself as one of the most complex and fascinating chapters in the history of our solar system. It demonstrates how the formation of giant planets can fundamentally alter the architecture of planetary systems, preventing some worlds from forming while enabling the formation of others. It shows us the crucial importance of timing in cosmic evolution, how the sequence and pace of planetary growth can determine which regions become populated with worlds and which become graveyards of planetary dreams. But perhaps most importantly, the asteroid belt reminds us that our solar system is not a static arrangement of planets in perfect order, but rather the product of billions of years of dynamic evolution shaped by gravitational forces operating across vast distances and enormous spans of time. In understanding how this seemingly empty region came to exist, we gain deeper insights into the processes that shaped our own world and continue to influence its destiny as it drifts through the cosmic dark, carrying with it the precious cargo of life that somehow managed to emerge from the chaos of planetary formation. The belt story connects intimately to our own existence, for without Jupiter's migration and the subsequent scattering of water-rich materials throughout the inner solar system, Earth might never have received the water that fills its oceans, or the organic compounds that may have contributed to the origin of life. In the scattered fragments that float between Mars and Jupiter, we see not just the remnants of worlds that never were, but also the delivery system that helped make our world what it is today. And so, as you drift towards sleep tonight, remember that floating out there in the darkness beyond Mars are the ancient witnesses to our solar system's violent youth. Each fragment, a library of information about the processes that shaped our cosmic neighborhood. They continue their eternal dance around the sun, these cosmic refugees, carrying with them the stories of formation and destruction, of migration and survival, of the delicate balance between order and chaos that determines whether dust becomes worlds or worlds return to dust in the endless cycles of cosmic evolution. The mechanisms that continue to shape the asteroid belt today operate on timescales that dwarf human comprehension, yet they follow patterns we can observe and measure with increasing precision. As you settle deeper into contemplation of these ancient processes, consider that every second that passes, countless interactions are occurring throughout the belt, each one contributing to the slow but relentless evolution of this cosmic population. The Yarkovsky effect represents one of the most elegant examples of how seemingly insignificant forces can accumulate into major changes over astronomical time. Picture a small asteroid tumbling through space, its dark surface absorbing sunlight during its day and radiating that heat back into space during its night. This thermal cycling creates a tiny but persistent thrust, like a miniature rocket engine powered by nothing more than sunshine and shadow. For objects just a few kilometers across, this thermal thrust is almost imperceptibly weak, producing accelerations billions of times smaller than Earth's gravity. Yet over millions of years, these gentle pushes can gradually alter an asteroid's orbit, causing it to spiral slowly inward or outward, depending on the direction of its rotation. It's a process so subtle that it wasn't even discovered until the late 20th century, yet it plays a crucial role in delivering meteorites to Earth and shaping the long-term evolution of the asteroid population. The beauty of the Yarkovsky effect lies in its size dependence. Very large asteroids are too massive for thermal forces to significantly affect their motion. Very small fragments are blown around by radiation pressure and solar wind in ways that overwhelm the thermal effect. But objects in the intermediate size, range, roughly 1 meter to 10 kilometers in diameter, exist in a sweet spot where thermal forces can gradually but persistently change their orbital energy. This size-selective transport creates a natural conveyor belt that moves material through the asteroid belt over geological time. Fragments created by collisions in the main belt can be slowly transported by thermal forces until they reach gravitational resonances with Jupiter, where they are rapidly ejected into Earth-crossing orbits. It's a process that connects the most violent events in the belt, the catastrophic collisions that shatter asteroids, to the gentle fall of meteorites in terrestrial deserts and Antarctica. The study of these delivery mechanisms has revealed that different types of meteorites reach Earth through different pathways, each with its own characteristic travel time from asteroid belt to terrestrial laboratory. Ordinary chondrite meteorites, which represent fragments of S-type asteroids from the inner belt, typically spend a few million years in space after being ejected from their parent bodies. But meteorites from more distant regions or from objects with unusual orbital characteristics can spend tens of millions of years wandering through the solar system before finally encountering our planet. These cosmic ray exposure ages, determined by measuring the accumulation of rare isotopes produced by high-energy particle bombardment, provide a kind of molecular clock that reveals the journey each meteorite fragment has taken from its parent asteroid to Earth's surface. The fact that we receive a steady rain of these space samples, each carrying with it a precisely measurable record of its travels, provides an unparalleled window into the dynamical processes operating throughout the asteroid belt. But the belt's evolution isn't driven solely by these gentle thermal forces and gravitational resonances. catastrophic collisions continue to reshape the population, creating new families of fragments while occasionally destroying objects that have survived for billions of years. The physics of these high-velocity impacts involves some of the most extreme conditions in the solar system, with pressures exceeding those in the Earth's core and temperatures hot enough to vaporize rock. When two asteroids collide at typical belt velocities of several kilometers per second, the impact creates a shock wave that propagates through both objects at supersonic speeds. The collision energy, concentrated into the brief moment of contact, can exceed the gravitational binding energy of the target by factors of thousands or millions. Under these conditions, solid rock behaves more like a fluid, flowing and deforming in ways that seem to violate our everyday understanding of how materials respond to stress. The outcomes of these collisions depend sensitively on the impact velocity, the angle of collision, the size ratio of the colliding objects, and the internal structure of the target. A glancing blow might excavate a crater and eject fragments without completely disrupting the target. A head-on collision between objects of similar size might shatter both bodies into thousands of pieces. The most energetic impacts can even vaporize portions of the colliding objects, creating impact plumes that expand into space at velocities exceeding the escape velocity of any asteroid. These collision outcomes create the complex size distributions we observe in asteroid families today. Mathematical analysis of family properties reveals that the fragment size distributions follow power laws that reflect the fractal nature of the fragmentation process. Large fragments are rare, intermediate-sized pieces are more common, and small debris is extremely abundant, creating a hierarchy of destruction that extends from kilometer-sized asteroids down to microscopic dust grains. The dust created by these collisions doesn't simply disappear into space. Much of it follows complex orbital evolution that can lead to its eventual capture by planets or ejection from the solar system entirely. Some dust grains spiral inward due to radiation pressure and are ultimately consumed by the sun. Others are swept up by the solar wind and carried to the outer reaches of the solar system. But a fraction of this debris finds its way to Earth, where it contributes to the constant rain of micrometeorites that adds roughly 40 tons of extraterrestrial material to our planet every day. These cosmic dust particles, often too small to create visible meteors as they enter our atmosphere, carry with them chemical signatures that reflect the composition and processing history of their asteroidal sources. The study of these micrometeorites has revealed unexpected diversity in the asteroid belt's dust population. Some particles show clear evidence of having been heated to high temperatures during their parent body's formation, while others preserve nearly pristine records of nebular condensation processes. The mixing of these different components in Earth's upper atmosphere provides a kind of real-time sampling of the entire asteroid belt population. Recent advances in analytical techniques have allowed scientists to study individual micrometeorites with the same precision once reserved for much larger meteorite samples. These microscopic fragments often contain mineral assemblages and isotopic compositions that are rare or absent in larger meteorites, suggesting they sample asteroid populations that are not well represented in our meteorite collections. The seasonal variations in micrometeorite composition that have been detected in some studies hint at the complex orbital dynamics that govern dust transport from the asteroid belt to Earth. Different source regions in the belt may contribute dust at different times of year, creating subtle but detectable changes in the composition of material reaching our planet. These observations connect the asteroid belt to Earth's environment in ways that extend far beyond the dramatic but rare impacts of large meteorites. The constant influx of cosmic dust influences atmospheric chemistry, contributes to cloud formation processes, and may even affect global climate patterns over geological time. In a very real sense, we are all breathing stardust, inhaling microscopic fragments of asteroids that have traveled millions of kilometers to reach our planet. The water content preserved in these dust particles tells stories about the hydration state of their parent asteroids. Some grains contain significant amounts of water locked in crystal structures, indicating formation under conditions where liquid water was present within asteroid interiors. Others are completely anhydrous, reflecting formation in environments where water was never present or was lost through subsequent heating. The organic compounds found in some cosmic dust particles are even more intriguing. These complex molecules, including aromatic hydrocarbons and even amino acid precursors, demonstrate that the chemistry of life's building blocks was operating throughout the asteroid belt during the early solar system. The delivery of these organic materials to Earth through micrometeorite bombardment may have contributed to the chemical inventory that enabled life to emerge on our planet. But the asteroid belt's influence on Earth extends beyond the direct delivery of materials through meteorite falls and dust accretion. The gravitational perturbations from the belt's largest members, particularly Ceres and Vesta, contribute to the complex orbital dynamics that govern the motion of smaller asteroids and comets throughout the inner solar system. These gravitational influences operate through a network of non-linear resonances that create what mathematicians call chaotic zones, regions of orbital space where small changes in initial conditions can lead to dramatically different evolutionary outcomes. An asteroid that begins its journey in a seemingly stable orbit might gradually wander into one of these chaotic zones, where its orbital evolution becomes unpredictable over long timescales. The boundaries of these chaotic regions shift and evolve as the orbits of the major planets slowly change due to their mutual gravitational interactions. What appears stable today might become chaotic millions of years in the future, and vice versa. This creates a constantly changing landscape of orbital stability that governs the long-term evolution of the entire asteroid population. Computer simulations that track the orbital evolution of thousands of test asteroids over millions of years reveal the complex pathways through which objects can migrate from stable main belt orbits to planet-crossing trajectories. Some pathways operate quickly, removing objects from the belt in less than 1 million years. Others work slowly, taking tens or hundreds of millions of years to gradually pump up orbital eccentricities until objects become unstable. The existence of these multiple timescales creates a kind of hierarchical structure in asteroid belt depletion. Objects that wander into the fastest acting resonances are removed quickly, creating gaps in the orbital distribution that are clearly visible in surveys of the asteroid population. But objects in more stable regions can survive for billions of years before eventually encountering the slower acting mechanisms that govern long-term orbital evolution. This temporal hierarchy helps explain why the asteroid belt has managed to survive at all. If all depletion mechanisms operated on the same rapid timescales as the most efficient resonances, the belt would have been emptied billions of years ago. Instead, The existence of both fast and slow removal processes has allowed a substantial population to survive in the most stable orbital zones, while continuously feeding material into planet-crossing orbits over the entire history of the solar system. The near-Earth asteroid population that poses an ongoing impact threat to our planet represents the current endpoint of this continuous delivery process. These objects, ranging in size from house-sized boulders to kilometer-scale mountains, are primarily escaped members of the main asteroid belt that have found their way onto Earth-crossing orbits through the complex web of gravitational and non-gravitational forces we've been discussing. The discovery rate of these potentially hazardous objects has accelerated dramatically in recent decades, as dedicated survey programs have systematically scanned the sky for moving objects. Each newly discovered asteroid adds another data point to our understanding of the delivery mechanisms operating throughout the inner solar system, while also contributing to our assessment of the impact hazard facing Earth. Statistical analysis of the near-Earth asteroid population reveals that different spectral types arrive through different dynamical pathways, reflecting the compositional structure of their source regions in the main belt. S-type objects, which dominate the inner belt, are preferentially delivered through resonances that operate most efficiently in that region. C-type objects from the outer belt follow different pathways that reflect the different dynamical environment in which they originate. This compositional sorting during transport creates subtle but detectable biases in the near-Earth population compared to the main belt source. Objects with certain orbital characteristics or physical properties may be preferentially delivered or preferentially destroyed during their journey from belt to planet-crossing orbit. Understanding these selection effects is crucial for interpreting observations of near-Earth asteroids and for estimating the true diversity of materials in the main belt. The rotational properties of asteroids provide another window into the physical processes that have shaped the belt over billions of years. The spins of most asteroids appear to have been randomized by countless collisions, creating a population with rotation periods ranging from a few hours to several hundred hours, and with spin axes pointing in all directions. But some asteroids show clear evidence for more recent spin evolution. Binary asteroids, where two objects orbit around their common center of mass, often show synchronized rotation periods that reflect tidal interactions between the components. Some asteroids spin so rapidly that they are close to the breakup limit, where centrifugal forces would overcome their gravitational self-attraction. The discovery of these rapidly rotating asteroids has revealed that many objects in the belt are not solid monoliths, but rather loose collections of fragments held together primarily by gravity. These rubble pile structures appear to be the natural outcome of the collisional processing that has shaped the belt throughout its history. When solid asteroids are shattered by impacts, the resulting fragments often reaccumulate into gravitationally bound aggregates that can survive subsequent collisions more effectively than their solid predecessors. The internal structure of these rubble pile asteroids creates fascinating possibilities for their long-term evolution. Material can migrate within the aggregate in response to thermal cycling, rotational acceleration, or impact disturbances. Some asteroids may be gradually shedding material from their surfaces as they slowly spin up due to thermal torques or tidal interactions with other objects. Recent observations have detected several asteroids that appear to be actively disintegrating. developing comet-like tails despite being located in the warm inner regions of the belt, where ice sublimation cannot be responsible for the activity. These observations suggest that some asteroids are so weakly bound that even minor perturbations can trigger the gradual loss of surface material. The study of these active asteroids has opened new avenues for understanding the physical properties and evolutionary processes operating throughout the belt. By monitoring objects as they shed material, scientists can probe their internal structures and surface compositions in ways that would be impossible through conventional observational techniques. The seasonal variations in asteroid activity that have been detected for some objects hint at the role of thermal cycling in driving surface evolution. As asteroids rotate and orbit the Sun, different portions of their surfaces experience heating and cooling cycles that can drive the expansion and contraction of surface materials. Over long periods, these thermal stresses can weaken surface bonds and make material more susceptible to removal by rotational forces or minor impacts. The colors and spectra of asteroids provide additional clues about the surface processes that have modified their compositions over billions of years. Space weathering, caused by bombardment by solar wind particles, cosmic rays, and micrometeorites, gradually alters the optical properties of airless surfaces throughout the solar system. On asteroids, this space weathering process appears to darken surfaces and redden their spectra over time, making old surfaces appear different from fresh material exposed by recent impacts. By mapping color and spectral variations across individual asteroids, scientists can identify regions where recent impacts have exposed unweathered subsurface material and estimate the rates at which space weathering processes operate. Some asteroids show dramatic color variations that reflect complex histories of impact excavation and surface renewal. Fresh crater walls and floors often appear brighter and bluer than surrounding terrain, indicating that space weathering effects can be reversed by impacts that expose pristine subsurface materials. The discovery of organic compounds on asteroid surfaces has added another layer of complexity to these space weathering studies. Some organic materials appear to be more susceptible to modification by space weathering processes than others, creating complex patterns of preservation and destruction that reflect both the original distribution of organics and their subsequent modification by the space environment. These surface processes connect the asteroid belt to the broader story of how small bodies evolve throughout the solar system. The same space weathering effects that modify asteroid surfaces also operate on the Moon, on comets, and on the small moons of the outer planets. By understanding how these processes work in the asteroid belt, scientists can better interpret observations of other airless bodies and develop more complete models of surface evolution throughout the solar system. The magnetic properties of asteroids provide yet another tool for understanding their formation and evolution. Some asteroids appear to be magnetized, carrying remnant magnetic fields that may have been acquired during their formation or through subsequent processing. These magnetic signatures can reveal information about the magnetic environment that existed in the early solar system and the thermal histories of individual objects. The lack of significant magnetic fields around most asteroids tells us that they never experienced the kind of core dynamo activity that generates magnetic fields in terrestrial planets. This absence of magnetic activity reflects both their small size, which limits the ability to maintain convective motion in metallic cores, and their relatively rapid cooling, which would have shut down any dynamo activity that might have begun during their formation. But some asteroids do show evidence for ancient magnetization, suggesting they formed in environments where strong magnetic fields were present. These fields might have originated from the solar nebula itself, or from magnetic dynamos operating within larger parent bodies that were subsequently disrupted by collisions. The study of these weak magnetic signatures requires sophisticated measurement techniques and careful analysis to separate true asteroid magnetism from the effects of solar wind interactions and spacecraft-generated magnetic fields. But when successful, these measurements can provide unique insights into conditions that existed during the earliest phases of solar system formation. As we drift toward the conclusion of this cosmic journey, remember that the asteroid belt continues to evolve even as you rest. Every moment, thermal forces are subtly pushing objects toward new orbital configurations. Collisions are creating new fragments while grinding others down to dust. Gravitational resonances are slowly but inexorably removing objects from the belt while delivering them as meteorites to Earth and the other terrestrial planets. These ongoing processes ensure that the asteroid belt we observe today will continue changing over the millions and billions of years to come. Some objects currently in stable orbits will eventually wander into resonances and be removed. New collision fragments will be created to replace some of those that are lost. The delicate balance between creation and destruction that has maintained the belt for billions of years will continue to operate, ensuring that this cosmic refugee camp remains a permanent feature of our solar system's architecture. The story of asteroid belt formation and evolution ultimately reveals itself as one of the most complex and beautiful examples of cosmic dynamics in action. It demonstrates how gravitational forces operating across vast distances and enormous spans of time can reshape entire regions of planetary systems. It shows us how the formation of giant planets can fundamentally alter the distribution of matter throughout their neighborhoods, and it reminds us that our solar system is not a static arrangement of objects frozen in time, but rather a dynamic, ever-changing system where forces continue to operate and evolve on timescales that dwarf human civilization. In the scattered fragments that populate the space between Mars and Jupiter, we see not just the remnants of worlds that never were, but also active participants in ongoing processes that connect the asteroid belt to Earth's environment and to the broader story of planetary system evolution. Every meteorite that falls to our planet, every grain of cosmic dust that enters our atmosphere, every near-Earth asteroid that crosses our orbital path carries with it information about these processes and reminds us that we are part of a larger cosmic community that extends far beyond our small blue world. And so, as you prepare to drift into sleep, know that you rest under a sky where ancient processes continue their eternal dance, where the gentle touch of sunlight can gradually alter the orbit of a mountain-sized rock, where collisions that occurred billions of years ago continue to send fragments on journeys that may one day bring them to Earth as messengers from the deep past. The asteroid belt remains active, dynamic, and full of surprises, a testament to the endless creativity of gravitational and physical forces operating in the vast darkness between worlds. Tomorrow will bring new observations, new discoveries, new insights into these ancient processes. But for now, you can simply rest in the knowledge that you are part of a universe where matter organizes itself into patterns of breathtaking complexity and beauty, where the same forces that scattered planetesimals across the early solar system continue to shape the cosmic environment in which we live, and where the story of formation and evolution continues to unfold in ways both subtle and profound throughout the endless expanse of space and time. Expanse of space and time. The resonance gaps that punctuate the asteroid belt like missing teeth in a cosmic smile tell perhaps the most compelling part of this formation story. These empty zones, swept clean by Jupiter's gravitational influence, serve as monuments to the power of orbital mechanics operating over geological time. When you map the distribution of asteroids throughout the belt, these gaps appear as dark valleys in what should be a continuous mountain range of rocky debris. Each gap corresponds to a specific mathematical relationship between an asteroid's orbital period and Jupiter's 12-year journey around the Sun. Objects that find themselves in these resonant locations experience regular gravitational tugs from the giant planet, like being pushed on a swing at just the right moment to make it go higher. Over millions of orbital cycles, these repeated nudges accumulate into dramatic changes in orbital shape and orientation, eventually ejecting objects from the belt entirely. The Kirkwood gaps, named after the astronomer who first explained their origin, represent some of the most dramatic examples of how gravitational resonances can sculpt the architecture of planetary systems. The gap at 2.5 astronomical units from the Sun, where objects would orbit the Sun exactly 3 times for every one of Jupiter's orbits, is so thoroughly depleted that it appears almost empty in surveys of the asteroid population. But these gaps aren't completely devoid of objects. Recent high-precision surveys have revealed that small populations of asteroids do exist within the resonances, following complex orbital paths that allow them to avoid the most destabilizing effects of Jupiter's gravity. These survivors represent asteroids that have found stable islands within seas of chaos, orbital configurations so precisely tuned that they can persist for billions of years, despite being surrounded by instability. The discovery of these resonant survivors has revolutionized our understanding of how gravitational resonances actually work. Rather than being simple zones of instability that eject all objects, resonances create complex landscapes of stability and chaos that depend sensitively on orbital parameters like eccentricity and inclination. Some combinations of orbital elements lead to rapid ejection, while others can remain stable indefinitely. This complexity extends throughout the asteroid belt, creating a hidden architecture of dynamical structures that governs the long-term evolution of the entire population. Computer simulations that track the orbital evolution of thousands of test particles reveal an intricate web of transport pathways, some leading to rapid removal and others allowing objects to migrate slowly between different regions of the belt. The three-body problem that governs the interaction between the Sun, Jupiter, and any individual asteroid creates mathematical chaos in the most technical sense of the word. Small differences in initial conditions can lead to dramatically different evolutionary outcomes, making it impossible to predict the long-term fate of any specific object beyond certain statistical limits. This fundamental unpredictability is built into the gravitational architecture of the solar system itself. Yet patterns emerge from this chaos when we consider large populations of objects rather than individual trajectories. The same resonances that make individual orbits unpredictable creates statistical flows that govern how material moves through the belt over time. These flows connect different regions of the belt to each other and to the planet-crossing populations that eventually reach Earth as meteorites. The near-Earth asteroid population serves as a kind of natural experiment in these transport processes. Every object in this population began its journey somewhere in the main asteroid belt before being perturbed onto an Earth-crossing orbit through the complex web of gravitational and thermal forces we've been exploring. By studying the orbital and physical properties of these objects, scientists can work backward to understand the source regions and transport mechanisms that delivered them. The discovery that different types of near-Earth asteroids arrive through different dynamical pathways has provided crucial constraints on models of asteroid belt evolution. Objects with spectra similar to ordinary chondrite meteorites, which dominate meteorite collections, appear to originate primarily from the inner portions of the main belt, but objects with more primitive, carbon-rich compositions that should represent samples from the outer belt are surprisingly rare among near-Earth asteroids. This compositional bias in the delivered population tells us that the transport mechanisms operating throughout the belt are not uniformly efficient. Some regions are more effective at delivering material to Earth-crossing orbits than others, creating selection effects that must be accounted for when interpreting our meteorite collections as samples of the asteroid belt population. The thermal forces that we discussed earlier play a crucial role in these transport processes, but their effects vary dramatically with object size, composition, and surface properties. Dark, carbon-rich asteroids absorb more sunlight and experience stronger thermal forces than bright, rocky objects of the same size. Rapidly rotating objects experience different thermal evolution than slow rotators. These variations create a complex size and composition-dependent transport network that preferentially delivers certain types of objects while leaving others stranded in the main belt. Recent theoretical work has revealed that the efficiency of these thermal transport mechanisms has changed over solar system history as the Sun's luminosity has gradually increased and as the asteroid population itself has evolved through collisional processing. Objects that were stable against thermal drift early in solar system history might become unstable today as the Sun has grown brighter and asteroid surfaces have been darkened by billions of years of space weathering. This temporal evolution of transport efficiency means that the meteorite flux to Earth has not been constant over geological time. Periods of enhanced delivery may have coincided with major changes in solar luminosity or with large collision events in the asteroid belt that created new populations of fragments susceptible to thermal transport. These variations in meteorite delivery could have influenced the evolution of Earth's atmosphere and biosphere in subtle but important ways. The water content of asteroids takes on new significance when viewed through the lens of these transport mechanisms. Water-rich objects from the outer portions of the belt face a longer and more difficult journey to reach Earth-crossing orbits than their dry counterparts from the inner belt. Yet the successful delivery of even small amounts of hydrated material during Earth's formation could have contributed significantly to our planet's water inventory. Recent analysis of hydrogen isotope ratios in terrestrial water compared to those measured in different types of meteorites suggests that Earth's oceans may indeed have received contributions from asteroid impacts, though the relative importance of asteroidal versus cometary water delivery remains a subject of active research. The asteroid belt's role as a source of Earth's water connects the story of its formation directly to the conditions that enabled life to emerge on our planet. The organic compounds preserved in some asteroids add another dimension to this connection between belt formation and terrestrial habitability. The delivery of these complex molecules during the late stages of terrestrial planet formation could have provided some of the chemical building blocks necessary for the origin of life. The fact that these organics formed within asteroid interiors, where liquid water and complex chemistry coexisted for millions of years, suggests that the asteroid belt may have served as a vast laboratory for prebiotic chemistry during the early solar system. The timing of organic synthesis within asteroids was governed by the same radioactive heating that drove differentiation in larger objects like Vesta. The decay of aluminum-26 and other short-lived isotopes provided the energy needed to melt ice within asteroid interiors, creating aqueous environments where organic chemistry could proceed over extended periods. This timing means that the most complex organic synthesis occurred during the first few tens of millions of years after solar system formation, exactly when terrestrial planet formation was reaching completion. And so, we reach the end of our cosmic journey through time, where fragments of ancient dreams continue their eternal dance in the darkness between worlds. The asteroid belt stands before us not as a simple collection of space debris, but as a profound testament to the delicate balance between creation and destruction that governs all cosmic evolution. In these scattered remnants, we've discovered the fingerprints of planetary migration, the scars of gravitational violence, and the whispered stories of water and organic compounds that may have seeded life itself on our small blue world. As you drift towards sleep tonight, remember that you are intimately connected to this ancient tale, breathing atoms forged in stellar hearts, living on a planet shaped by the same forces that prevented other worlds from being born, part of a universe where mystery and wonder dance together in perfect eternal harmony.